Autoencoders are neural networks trained to reproduce their input at the output. By forcing information through a constrained internal representation, they learn to capture the essential structure of the data without using labels. They are a foundational tool for representation learning where the goal is not prediction but discovering structure in data. By reconstructing inputs under constraints such as limited dimensionality or noise, they learn compact, reusable representations. And so I want to start with these definitions where we have to understand that an autoencoder is really a neural network trained to attempt to copy its input to its output. And it consists of two components. One is an encoder function, and you can see this in this illustration where from the input the neural network goes layer by layer until it gets some sort of an internal representation that we are going to refer to as latent space or representation through latent variables, or we are going to call this the result of the encoder, the encoded data. And we denote this the encoder function by f, and for the input x, the embedding through this encoder function is going to be h. And then the second part of the neural network is a decoder function. That's another neural network that takes as an input this latent representation of the input and is going to decode it and hopefully reproduce the original input. So we are going to denote the decoder function by g. That's going to be applied to these latent variables, and we are going to denote the output of that function as r. And so the goal of this neural network is to minimize the difference between the input and the result of the neural network once it goes through the encoder function and then through the decoder function. So why is this useful? Because if you think about it, the idea that a neural network or a model in general is going to just make a lot of computational effort to just reproduce its input to the output is not obvious that this has any significant applications. But once you think about it in terms of this model learning to reproduce the input, even if it's perturbated, for example, by noise, you realize that all of a sudden this has significant applications in terms of denoising. And also this is going to have applications in terms of generative models, and that's not exactly obvious on this slide how it's going to go, but we are going to come back to this throughout this lecture. The internal representation that we denoted here by h is going to offer some sort of an encoding of the input, or is going to learn some key aspects of the input, and that can be phrased in terms of feature learning. Now obviously the idea that we would have these autoencoders is really about getting these useful properties. And obviously we don't want to have the encoding equal to the input. We would like to have just the key properties of the input represented in this encoding. So in other words, we want this encoded vector to have a smaller dimension than the input. And so in other words, reproducing the input into the output is not really the real goal of these autoencoders, but rather is to learn these representations that encode hopefully useful properties of the input. And through neural networks or some other types of models, but neural networks are really at the moment the most popular versions of these, you have some nonlinear functions for the encoder and the decoder. And the idea is that you would want to limit somehow the capacity of the encoder, because if you don't do that, then you can easily imagine that the encoder has so much power that it really just rephrases the input, and that's not really what you're after. You want to just extract some of the key properties of the input. So you want to limit this capacity, for example, in terms of having smaller size or in some other ways that we are going to discuss. So this idea of limiting the capacity of the encoder leads to the concept of regularizing autoencoders. And this regularization can be of many different types. We mentioned on the previous slide that you want to have a smaller dimension of the embedding as compared to the dimension of the input, but you can also think in terms of sparsity, for example, the idea that out of those latent variables, just a small number of them are active for any given input. You can also think in terms of small derivative of the representation, and also in terms of being robust to noise and to missing inputs. And we're going to open this up, each one of these ideas. So if I take first the idea of the sparse encoders, the goal here is that you would like to constrain the latent representation to be sparse in terms of the most latent units to be inactive for any given input. And so the question, in terms of mathematical optimization, how to enforce sparsity, the most common approach is that you are adding to the loss function being the difference between the output of the encoder plus decoder with respect to the input. So you are adding to the loss function a penalty on the activations of the code layer. So you have this part, this is the loss in terms of your autoencoder being able to reproduce the input. You are adding this term, and this can be, for example, an L1 penalty on the layer that gives you the latent variables. And if you think about this in terms of what the L1 penalty is, and you realize it's a sum of the modulo of the activations, and you want to impose those to be as small as possible, you realize that in some sense this is a softer version of winner takes all. It's not as hard of a choice as you have in competitive learning, where you ask that only one is non-zero and all the other ones are zero, but you are asking that overall the sum is somewhat small. So this can be thought of in terms of a softer version of winner takes all. And this is a very modern and popular approach to autoencoders nowadays, and typically this is implemented through ReLU activations in each one of the layers, and in the latent variable layer via L1 penalties or L2 penalties. Here is another form of an autoencoder, and that is denoising autoencoders. And so if you think about the traditional loss function in autoencoders, the idea that you would want the autoencoder to be able to reproduce as much as possible the input, so you would have in terms of the loss function the difference or the norm between the input vector and the output of the neural network. Here, when we go to denoising, the concept is that if you are given a noisy version of some input, you would like your neural network to be able to identify, generate the denoised version of the input. So in other words, what you want to have in terms of a loss function is you have the difference between your vector and the output of the network on some sort of a noisy variant of your input. And the way you go about implementing this is that you have an input and you are passing through the network some addition to your input. You are adding some randomly generated Gaussian noise. And so with this sort of idea, you are going to have as an objective the concept of learning to denoise or to undo some form of data corruption. Here is another form of regularization in autoencoders, and that is by penalizing derivatives. And again, here the general concept is the same to the traditional, loss function that you see in most autoencoders. You have this additional loss function, but in this case, this loss function is going to be the partial derivative of the latent variables with respect to the input. And the reason why partial derivatives could be relevant, depending on the problem that you want to solve, is that they really give you the concept of learning a function that doesn't change much when the input changes slightly. That's exactly what this concept of derivatives is. It's just a measure of how much this hidden layer, this latent representation, changes if you have some small changes in the input. This is also called sometimes contractive autoencoder, and the keyword here, contractive, comes from the idea that a neighborhood of input points is mapped to a smaller neighborhood of output points. One other very popular form of autoencoders is that of variational autoencoders, and here the concept is somewhat different. Whereas in standard autoencoders we have deterministic encoder, decoder, so in other words we have some functions for the encoder and the decoder, so you have an input and that's associated to the latent representation h of x, and that's really then mapped into the output of the neural network that hopefully is not too far from the input. In variational autoencoders, the idea is that you get rid of this deterministic encoder-decoder and in fact you replace it with a probability distribution. So you would have instead a stochastic encoder-decoder, and the mapping is going to be from the input to a full probability distribution. And then this probability distribution, you are going to sample and get just one sample of that, and then you pass through the decoder, and the decoder is going to give you in the output another probability distribution. So all of these, sound like a drastic departure, but in practice what happens is that the latent representation very often is going to be assumed to be of a certain form. Typically, it's going to be assumed to be of a Gaussian form, so you will assume a normal representation. And the goal of the encoder is going to be to just learn the parameters of this probability distribution. Very often you are going to assume that these latent representations are having mean 0, and the job is going to be to estimate the variance. Sometimes maybe you want to also assume something else than 0, so then the task is going to be extended to learning also the mean of the distribution of the latent variables, and it's going to be the same in terms of this output representation. So the way this is going to go is that again you are going to from the input to the through the encoder you are going to learn these variables, the mean and the variance of the encoder. And then you are going to get just a single sample from that probability distribution, and you're going to pass that through the decoder. And the decoder is then going to have a similar task to learn the parameters of this output distribution. Autoencoders have found a number of very exciting applications. For example, they have applications in terms of dimensionality reduction. For example, if you think about these latent representations in terms of just bidimensional or tridimensional representations, then all of a sudden you can get a visualization in terms of a 2D or a 3D plot. And the key idea here is that release this latent layer. That's the goal of the whole effort of training an autoencoder. Just the idea that you reduce the dimensionality of the input to these 2D, 3D representations. The original motivation for autoencoder was in terms of feature learning, or if you want, in terms of representation learning. And the idea that once you get this latent representation, you are going to be able to pass it downstream for other machine learning tasks. For example, you are going to train another classification model or another clustering model on top of these latent representations that you've learned through your autoencoder. Then, as we anticipated on the in the beginning of this video, we have applications in terms of denoising or signal restoration, and the typical use for this is in terms of image or audio denoising, or any form of data that comes from a physical device. For example, biomedical data pre-processing, but really any data that comes from a physical device and unavoidably has noise, and you would like to remove that noise. Then we also have applications in terms of anomaly and novelty detection. where the key idea is that you're going to train your autoencoder on what you consider normal data only. So, for example, access to a web server, and you're going to train the autoencoder just on this sort of normal, user habits, sort of access to the server. And then the hope is that the reconstruction error is going to be high for anomalies, something that the model has not been trained to see in terms of normal data is going to be highlighted in terms of a high reconstruction error. And then finally, I want to mention here what has become very popular in terms of generative modeling. And the typical example here is that of a variational autoencoder. And the concept here is that your latent representation is a probability distribution. So you can just use the second part of your autoencoder, for example, the decoder, and you can just generate any number of samples in terms of the distribution of the latent representation and pass them through the decoder to get synthetic data that really should be somewhat similar to the input that the model was trained on. So typical usage for these sort of applications are in terms of image synthesis and also in terms of data augmentation.